Kinetics? What are those, like chemical kinetics? I assume so. Today on the drawing board by TBPi, we will be figuring out what are kinetics and how we can use them to help us in chemistry and to discover more about chemical reactions. So what are kinetics? Kinetics come down to telling us how fast a chemical reaction proceeds forward. So in many cases, this is given to us in concentration per time. And when it is in that, we call it a rate. So an example rate, if we had 1 mole per second of a substance being gained, we would call that then concentration moles per liter over time per second, putting us in final units of moles per second. And that's commonly where we will see rates written. So when we're referring to a rate, you'll see it as the symbol little RA. So that A can be switched out for whatever substance you have. So if we had the rate of CO2, that would be written as rate CO2, or whatever substance you have. Now, rate laws can commonly be written based on the stoichiometry of a reaction. Now, we'll get more to that later, but that is something we call an elementary reaction, and that makes finding our rate very easy. Finally, our rate is really used most commonly to find the speed of a reaction. Since we're looking at concentration per time, it's essentially the speed of how fast we are gaining reactant or products, or how slowly we are losing reactants. So the best way to learn about rate is just to take a look at a reaction and we'll write out how we look at the rate for it. So we have one of the most simple reactions here. This is just 2 hydrogen and an oxygen forming 2 H2Os. So in order to write a rate, we want to get this in terms of concentration per time. So in order to do that, we're going to want to start by picking a substance. So we'll take H2 here, and we'll start by writing a rate for that. So our rate is going to be written as negative R of H2, since this is the rate of hydrogen. And we're going to put a negative out there since our reactant is being consumed. So this is a negative rate of production of hydrogen. Now we're going to set that equal to the change in concentration of hydrogen over the amount of time it takes us to make that change. And that, in its simplest form, is how we can find a rate. But we also have something that is our rate of the reaction. You'll often just see that written as R for the reaction. In order to find that, we're going to take our rate and set it equal to the same thing we had earlier, delta CH2 over delta T. But now we need to look at our stoichiometric coefficients. So for this R, we want it to be of our lowest stoichiometric coefficient. In that case, this is oxygen with a 1 rate here. So in order to get this 2 down to a 1, we're just going to put a 1/2 outside of this term. Now the cool thing about rate of reaction is we can do the same thing for all of our components and we will get the same rate or the same number. So for O2, we first look at this number in the front. So since it's already a 1, we can just leave it a 1, so we won't bother writing that. Put delta concentration of O2 over the change in time. And now this is going to be the same as for O2. So since we have this 2 in the front, we're going to put a 1/2, then delta concentration H2O over change in time. Now we do have one problem here. These two, your reactants, are being consumed while your product is being produced. So therefore your rate needs to reflect that. So as our concentration of hydrogen goes down and our concentration of oxygen goes down, our water concentration is going to be going up. So to account for that, we'll just put little negatives outside of both these terms to represent that these are being consumed while that's being produced. And that is the simplest way to write out the rates for a given reaction. So now that we took a look at an example, let's get the most general form of writing a rate that we can. So given this very general reaction, so the little letters are representing our stoichiometric coefficients here, and then the big letters are our species. How can we write a rate law for something as generic as this? Well, we're going to do exactly what we did before. Little r, or a rate for reaction, is equal to 1 over the stoichiometric coefficient of the first one, so it's little a, times delta concentration of A over the change in time. Now, since this is a reactant and it's being consumed in this reaction, we're going to put a negative out front. As we did before, we can do the same thing for all of our reactants and products. So for B, just 1 over little b, the stoichiometric coefficient, times the change in concentration of B over the change in time. Now as we go over to the other side here, we're going to keep these positive since we are creating C instead of consuming it. But other than that negative sign, everything stays the same. And D is going to look exactly the same as C does. We come out with a very generic equation exactly like that. So many different ways for us to solve for the rate of a reaction. So now that we've solved for rates of reaction, what are we going to use those for? So right here, as you can see, we have a very simple reaction, just A going to B, and we have made a plot of concentration versus time. So this green line here, that is our reactant A. So as you'll notice, we start very high concentration, and as we react, we are losing A as it is consumed to make B. But on the other hand, you'll notice B, we start with a very low amount, and it just gets higher and higher as we create more B. You'll also notice that as we go along, these curves starting to flatten out. It's because as we start to run out of A in our solution, there's nothing else to react to create B. So when we are completely out of A, B can't keep rising. So naturally, as we make more B, we lose more A until eventually they both flatten out when there's no A left. So since rate is constantly changing, there's a few different rates we like to look at. The first one is called the instantaneous rate. So this is the rate at any one time. So for our sake, let's say we want to know right here what our rate of consumption of A is. All right, well, what we'll do is we'll go up to this curve, make a point right there. And then what we're going to do is we'll draw a tangent line through that point. Now, if we actually had scales on our graphs, we could find the slope of that line, and the slope is then equal to the rate. You'll notice that's what's cool about these plots, is anytime on a concentration versus time graph, if we have a slope of a straight line, that is the rate that we are looking for. So that's an instantaneous rate. And how about an overall rate? So let's say we wanted to know our overall rate from this time right here to this time right here, our rate of consumption of A. So we're going to start the same way we did for the last one. Go up to our curve and make a line. Same thing up here, make a line. And then you guys are going to just draw a straight line through those 2 points. And then you can take the slope of this new line you just drew, and that will be what's known as your overall rate, or your rate between two different time values. And finally, you're going to have your initial rate. This one is pretty self-explanatory. It is your rate right at the beginning. So for, once again, looking at our rate of consumption of A, we just make a point right at the top, draw our tangent line, and then find the slope of that line, and you can get your initial rate. So we've learned how to calculate rates at a specific time, but as you saw in this plot, the rate is constantly changing based on our concentrations. So what if we want to know the instantaneous rate without needing to draw this whole chart out? Well, there's a way we can do that, and that's called a rate law. So you'll generally see a rate law written in the form R equals K times the concentration of A to the alpha times concentration of B to the beta. Now specifically, that is for the reaction A plus B yields C plus D. So what exactly are all these terms here? So this R, we've already learned about. This is our rate, just like it was before, but now this is our instantaneous rate. This K is what is known as a specific reaction constant. We'll talk more about that in a little bit. The CA, we've already talked about. This is our concentration of A. It's the same thing for CB. This is our concentration of B. And now this alpha and beta are what are known as the order of each reactant. So order essentially tells us how we can compare how quickly we are losing a reactant to how quickly we are gaining a product. Generally, these orders have to be found experimentally. So you do the reaction, changing A and changing B, and doing that, we'll be able to find the different orders of these. We'll do an example of that in just a little bit. But there's one more way we can often find these orders, and that is if our reaction is known as an elementary reaction. So what is an elementary reaction? There's a ton of requirements out there that you guys can go find on your own time, but essentially an elementary reaction means we can take the stoichiometric coefficients and make those our order. So in this reaction, that's the same reaction we've been looking at. We just now have some stoichiometric coefficients in here. If this is indeed an elementary reaction, we know that Ca is of 8th order, and we know that Cb is of bth order. And this can go for any numbers of order you have there based on your stoichiometric coefficients here. So if we have this elementary reaction, it is much easier for us to find the order than needing to do this all experimentally. So how about this last part we haven't talked about, K? Well, K is what's known as our specific reaction constant, and K is specific to each individual reaction. So K can change to any number based on the reaction and based on the temperature. And that's one of the things that makes K very unique. K is temperature dependent. So due to this, we'll often need to change our K values if we are running at different temperatures for our reactions. But what's cool about K is we can often use K to compare the rates of two different reactions. Generally, a higher K means that we will have a higher rate or speed of the reaction. So if we have a really big K value, we'd expect our reaction to form our reactants into products very quick, versus if we had a very small K value, it would take much longer for us to get to our products. One other unique thing about K is its units will change based on the order of our reaction. So most commonly, we will see reaction orders at 0, 1, or 2. So 0 order means that our reaction rate is not impacted at all by our concentration. First order means we will generally only have one reactant to the first power here, so like alpha would be 1. Second order generally means we either have 2 reactants or we have 1 raised to the second order. Now for each of these, K has different units. So if we have a 0 order reaction, this becomes equal to moles per liter second, which is also our general units for the rate. If it is first order, we see it just get into per seconds, or it could be per minutes. It's per time, commonly seen as per second though. In the second order, we will see it in liters per mole times second. So one little key, if you're ever given a K value on some sort of an exam, you can look at the units, and that can often help you to discover what your rate is of the overall rate law. So now let's determine some orders based on experimental results. So here in front of me, we have a table of the following reaction. A plus 2B yields C plus 2D. We did an experiment 4 times, each time changing the values for the initial concentration of A and B. And then over here, we have the initial rate of formation of C. Different values for each one of these. So what we're going to want to do is go through and use these to find our orders for our rate law. So again, just to remind you, rate law is written in the form R equals K Ca alpha times Cb beta. So let's take a look at this experiment. So initially we have 0.1 moles per liter of each of our reactants, and here's our initial rate. Now next what we do is we triple the amount of each, and this gives us a new rate of formation. However, since both reactants were changed here, this data point doesn't help us very much, at least right now for determining the rates of A and B. So let's check the next experiment. Next experiment, A is now the same as above, but B has now changed from experiment 1. However, we can see over here, the initial rates of formation have not changed at all. So we've tripled the amount of B, but there's no change in rate. What that tells us is that the order of B has to be equal to 0, since this rate of formation did not at all change. So now, let's take experiment 3 here, and if we look back up to experiment 2, you'll notice we have the same amount of B in both of these. So let's compare our A's. So we have tripled the amount of A from experiment 3 to experiment 2. We've seen our rate of formation triple as well. So we had our concentration triple and our rate triple. That means our order of A, which is alpha, is equal to 1. And now that we know that, we can write our basic form of the rate law. So we can say the rate of this reaction is equal to K times Ca to the first power, so we'll leave that out. And then we could say times Cb to the 0 power. Of course, anything to the 0 power is 1. So we can rewrite that as R equals K Ca. So in this reaction, even though B is a reactant, since it is 0 order, it does not get included in the final rate law. So as we said earlier, this value of K has to either be determined experimentally or through some very weird correlations that we won't get into. But what is easy to find is K when we find a temperature change. So for example, if we ran the reaction at say 350 Kelvin, and then we said we wanted to run it again at 400 Kelvin, to bring our speed up, how much faster would we be? Well, our concentrations wouldn't change. The only thing that would change is our K value. So luckily, instead of needing to go redo experiments, we have a correlation to tell that to us. So we can say that any K value is equal to a constant A times E, or an exponent, to the negative EA, that's activation energy of the reaction, over R, which is our ideal gas constant, times T, or the temperature. So we're left with this weird A here. So to find A, what we're going to use is use a known value of K. So generally, we'll know the activation energy for a reaction. We'll know a K at a specific temperature. So we can use those two plus the R value and the temperature we're at to find A, and then plug A back in to find our new value of K. So let's do an example to show you guys what that means. So right here, we have the reaction we'll be working with. Simple A plus B yields C. And we want to know its rate law at 350 Kelvin, assuming it's an elementary reaction. So we have a K value here, 5 times 10 to the 5th liters per mole second at 400 Kelvin. And we also are given an activation energy, and that's out of any simple literature source. So let's start by finding our rate law in terms of just generic K. We'll come back and find our K in a second, but let's just start by finding the rate law. So we know it's an elementary reaction, so that makes our life really easy. We can just use the stoichiometric coefficients of our reactants to find our products. So we're going to say negative RA, so that's our negative rate of consumption of reactant A, is equal to K, which is that constant, times CA, and then alpha, our order is 1, times CB, where our order is also 1. So as we said earlier, to double check that, we can look at our units on K, which is in liters per mole per second, which if you remembered earlier, shows a second order reaction. And if we add up our orders here, 1 and 1, we get 2. So this is a second order reaction, so that checks out. So now let's find our K value. As easy as it would be for us just to take this 5 times 10 to the 5th liters per mole second, unfortunately that's not at the right temperature. This is at 400, and this is at 350. So let's write out that equation from earlier to change the temperature of our K. K equals A, E to the negative activation energy, EA, over R times T. All right? So we're going to start by finding this A value with our K value that we know from up here. So if we plug in 5 times 10 to the 5th liters per mole times second is equal to A, which we're going to solve for, E to the negative activation energy, which we have up here, so that'll become negative 40,000 joules per mole. I'm going to put that over R times T. So let's talk about R for a second. Of course, R can have a ton of different values since it's the ideal gas constant. But here, since this is in joules per mole and our temperature will be in Kelvin, we want to use the ideal gas constant that's in units joules per mole times Kelvin. So if you guys don't know this, there's a great page on Wikipedia that shows a ton of different ideal gas constants. Don't listen to your professors, Wikipedia is great. So when we look there, we find our value of R to be 8.314 joules per Kelvin mole. And we're just going to multiply that by our T for this K value, which is 400 Kelvin. You'll solve that all for A. Once you go through and do all that, you'll get an A value that is equal to 8.37 times 10 to the 10th. So that's great, but that doesn't need to go up into our rate equation. A new K value does. So now we can use this equation again to find a K value at 350 Kelvin. So let's rewrite our equation. K equals AE to the negative EA over RT, exactly the same as before. So now what we're going to do, we're going to leave this K as a variable, but now we're going to call it K350, since it's at 350 Kelvin. Set that equal to our A value, which is 8.37 times 10 to the 10th times E to the negative 40,000 joules per mole. Put that over that same R value, that 8.314 joules per Kelvin mole. Multiply that by our new T value, so our final T value up here. We're going to multiply that by 350 Kelvin. Now you can go through, this is just simple, plug it into your calculator, and you will get K350 to equal 8.97 times 10 to the 4th. And our units here will be the same as our units were up here. So that leaves it in liters per mole second. All right, we now have K. We have the rest of our rate law. So we can write out our final rate law now. So we can say negative RA, so again, is our rate of consumption of A, is equal to 8.97 times 10 to the 4th. That's our K value, times CA, to keep as a variable, times CV, to keep as a variable. And that right there is your final solution. So just real quickly in conclusion, there's one thing you remember about rate laws. Remember that form right there. RA equals K CA times CB. Now, more specifically, the rate law isn't really just K times CA CB. It is K times CA alpha times CB beta. So where, of course, those alpha and betas are orders which we will generally discover via different experiments. So coming over here now, this RA over delta C over T, just never forget that that is our basic form of a rate. is just a change in concentration over time. And of course, we can always find that change in concentration over time if we know the rate law from up here. And finally, if we ever have a k value that we don't know, we can always look down here to our final equation to find it, that k equals ae over negative ea over rt. And thanks for watching. We hope you join us next time on the Drawing Board by Tau Beta Pi.